Change in enthalpy. Enthalpy is denoted with a capital H. It is a state function, which means that the change in enthalpy is independent of the pathway. So for chemical reactions, the change in enthalpy is simply the enthalpy of the products minus the enthalpy of the reactants, or by the system. If the change in enthalpy is less than 0, negative, that means it's exothermic. Heat is released by the system. So again, the change in enthalpy is simply just Q for constant pressure situations. For example, when solid sodium hydroxide pellets are added to water, the following reaction takes place. Sodium hydroxide solid goes to sodium hydroxide aqueous. For this reaction at constant pressure, the change in enthalpy is negative 43 kilojoules per mole. If 14 grams of sodium hydroxide is added to water, A, does the beaker get warmer or cooler? Well, the answer here is all in the sign. They give us that delta H is negative. Therefore, negative means exothermic. Heat is released. Therefore, the beaker will get warmer. B, is the reaction endo or exothermic? Again, negative sign means heat is released, therefore exothermic. C, what is the enthalpy change for the dissolution? Well, they're giving us in the problem that it takes or it releases 43 kilojoules per mole of sodium hydroxide dissolved. If we had 1 mole of sodium hydroxide and dissolved it, 43 kilojoules would be released. But we didn't have a mole, we only had 14 grams of sodium hydroxide. So we want to find out the enthalpy change for this reaction. The first thing we have to do is change 14 grams of sodium hydroxide to mole, so we'll know how much of a mole we dissolved. Then we can just multiply the moles by this 43 kilojoules. So here's what I've done. I've taken 14 grams and changed it to moles by dividing by the molar mass of sodium hydroxide. Now that we're in moles, cancel out the grams here, negative 43 kilojoules per mole is the enthalpy change. So when we do the math, we get 15 kilojoules, and that's the delta H, or enthalpy change, for 14 grams of sodium hydroxide undergoing this reaction. Next example, consider the combustion of propane. Given by this reaction, the delta H is negative 2,221 kilojoules when 5 grams is burned in excess oxygen. So assume that all of the heat comes from the combustion of propane. Calculate the enthalpy change in which 5 grams of propane is burned in excess oxygen at constant pressure. We are given that the delta H here is this for 5 grams. We want to find the delta H. Take a moment to pause the video and work this problem out for yourself, because this is very similar to the one that we just did. Okay, so to solve this problem, we're given that the delta H is negative 2,221 kilojoules per mole of propane. But we only had 5 grams of propane. So we need to find out how much of a mole this actually is. So let's change 5 grams of propane to moles. We have to find the molar mass of propane, and that is 44 grams. We're in moles now, so we just multiply by the enthalpy change, or the delta H. So we know that negative 2,200, we get negative 252 kilojoules for this reaction. And that's our delta H for 5 grams of propane. These reactions that we've discussed so far are examples of constant pressure calorimetry, since atmospheric pressure remains constant throughout the process. This is an example of a coffee cup calorimeter as you used in lab. Calorimetry is simply the science of measuring heat changes. In order to do calculations with calorimetry, we need to define specific heat capacity. It's simply how much energy it is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. We can use either the specific heat capacity or the molar heat capacity. The molar heat capacity has a similar definition. It's just how much energy is required to raise the temperature of 1 mole of a substance by 1 Celsius degree. This is the CP, or the C, in Q equals MC delta T that you've used in the past. Heat is equal to the mass times the specific heat of the substance that you're dealing with times the change in temperature. The C is the specific heat. Now, if two reactants at the same temperature are mixed together and the resulting solution gets warmer, this means the reaction taking place is exothermic. An endothermic reaction gets cooler as it takes place, or it cools the solution. Now let's go back to that formula we talked about just a second ago. To remind you what everything stands for, the Q is in joules, and that's heat released or gained by a reaction. M is mass. C is the specific heat. It's specific for the substance that we're dealing with. And it's how much heat is required to raise the temperature of 1 gram by 1 degree. And then delta T is just the temperature change the substance goes through, and that's in degrees Celsius. Let's try a few sample problems. 100 grams sample of water at 90 degrees is added to a 100 gram sample of water at 10 degrees. The final temperature of the water is what? You can work this problem without really using any math. They tell you that you have equal amounts of water. They're both the same substance. One is at 90 degrees and one is at 10 degrees. So if you mix these two substances together, you can expect that the temperature will be exactly in the middle between 90 and 10. Warm water, the heat lost by the warm water is equal to the heat gained by the cool water. So the heat lost by the warm water is equal to MC delta T. The heat gained by the cool water is equal to MC delta T of the cool water. If the masses are the same, 100 grams and 100 grams, you can cancel. Since both the substances are water, the C will be the same, 4.18, so we can cancel that. The only thing left in the equation is delta T, which must be equal. So therefore, the delta T will be the same, so the temperature will end up exactly in the middle here. Correct answer is B. Next example, 100 gram sample of water at 90 degrees is added to a 500 gram sample of water at 10 degrees. So let's draw the picture here. You have 100 grams of water at 90 degrees, and you have a 500 gram sample of water. This is not drawn to scale, obviously, at 10 degrees. What is the final temperature of the water? Well, let's say the warm water, MC delta T of the warm water is equal to MC delta T of the cool water. So we put 100 grams for our mass. Water is specific heat is 4.18, as you know. We'll leave the delta T blank for a second. The mass of the cool water is 500 grams. The C of the cool water is 4.18, and the delta T will leave blank. Now, to find the delta T, you know that the warm water is at 90 degrees and the cool water is at 10 degrees. So you know when you mix these two samples of water, we'll end up somewhere in between, but we're not sure. The final temperature of both will be the same. So we'll call that T final between the 90 and the 10 somewhere. We'll call that X. So the expression for the warm water delta T, it started at 90 and ended up at X. So 90 minus X. We can put that here. The warm water goes through 90 minus X. The cool water heats up to some final temperature X. So we can say the delta T of the cool water is X minus 10. Now we have those expressions. All we have to do is solve for X. And when you solve for X, you'll find that X equals 23 degrees. So the correct answer would be between 10 and. This problem is similar to the lab that you did. You have a styrofoam cup with 50 grams of water at 10 degrees. You add a 50-gram iron ball. We'll make it a chunk instead of a ball. 50 grams. Which is at 90 degrees, to the water. We want to know the final temperature of the water. So we know that the heat lost by the metal will be equal to the heat gained by the water. So for the water, the heat gained by the water, the Q of the water is equal to the Q of the metal. So we write expressions for both. MC delta T for the metal is equal to MC delta T for the water. We know that the water is 50 grams. The specific heat of water we know is 4.18. And the delta T will leave blank for now. The metal mass is 50 grams. The specific heat of iron they give us is 0.45. And the delta T will leave blank. Now, we need to write an expression for the change in temperature for both the water and the iron. We know that the iron was originally at 90 degrees and the water was at 10 degrees. The final temperature is somewhere between, we'll call X. So the expression for the metal, the delta T is 90 minus X. That'll give us the delta T for this. So 90 minus X. And for the water, X minus 10 will give us the delta T. Now we simply solve for X. And when we do that, we find that X is equal to 18 degrees. Now we'll have one last example of constant pressure calorimetry. Remember that delta H is equal to Q. Okay, so when 1 liter of 1 molar barium nitrate solution at 25 degrees is mixed with a 1 liter of 1 molar sodium sulfate solution at 25 degrees in a calorimeter, the white solid barium sulfate forms and the temperature of the mixture increases to 28.1 degrees Celsius. Assuming that the calorimeter absorbs only a negligible quantity of heat, that the specific heat capacity of the solution is 4.18 and the density of the final solution is 1 gram per milliliter, calculate the enthalpy change per mole of barium sulfate formed. I've written the equation here, barium nitrate plus sodium sulfate. We're told that barium sulfate solid forms and sodium nitrate is the other product. We are given in the problem that we have 1 liter of barium nitrate of 1 molar solution. So if we have 1 liter of 1 molar, we know that molarity times volume equals moles. So molarity times volume, we got 1 mole of barium nitrate. The same thing for sodium sulfate. We're given that 1 liter of 1 molar sodium sulfate was added. Again, molarity times volume equals moles, so we got 1 mole of sodium sulfate. In this case, because the equation is balanced with simply ones, we can see that it's a 1 to 1 to 1 ratio. So we have 1 mole of barium nitrate combining with 1 mole of sodium sulfate, we're going to get 1 mole of barium sulfate. So this is perfectly written so that we will be able to see the molar delta H, or the molar change in enthalpy. Since 1 mole is formed, however much heat is released by this reaction will give us per mole. I went ahead and wrote the net ionic equation for this. It's given here, 1 to 1 to 1 mole ratio. Now, the temperature increased, therefore we can determine that the reaction is exothermic, because we went from 25 degrees, both of our solutions were at 25 degrees, and it increased to 28.1 degrees. So the reaction's exothermic. The heat evolved by the reaction, or Q from the reaction, is equal to the Q absorbed by the reaction. So MC delta T will give us what we're looking for. So to find the mass of our solution, we need to know the total volume of the solution. We know that 1 liter of solution has a mass of 1,000 grams because 1 milliliter of water has a mass of 1 gram. They gave us in the problem that the density of this solution is 1, therefore we can assume that 1 milliliter is equal to 1 gram. We just need to know the final volume. Well, we're told that 1 liter of barium nitrate is combined with 1 liter of sodium sulfate. Therefore, we have 2 liters of solution. If we have 2 liters of solution, we can assume that is 2,000 grams. Total volume of solution, 2 liters. 1 liter of each reactant was used. The density of solution is 1 gram per milliliter. So we can go ahead and assume that 2 liters equals 2,000 grams. So now we have our mass, 2,000 grams. We're also given in the problem that the specific heat of the solution is 4.18, same as water. So now we have the specific heat. So if we plug in all of our numbers that we're given, 2,000 is our mass, 4.18 is our specific heat, and they gave us the final temperature was 28.1. Subtract that from 25 from that, and that'll give us 2.6 times 10 to the 4th joules. We want that in kilojoules per mole. And we know that 1 mole of each substance was used and 1 mole was of our product was made. Therefore, we can just say, change that to kilojoules. We get 26 kilojoules evolved. Therefore, since 1 mole was made, our delta H is 26 kilojoules per mole. Now, if this problem had given us more than 1 mole, we would have needed to adjust our answer based on the number of moles, as we have in previous